Well, greetings again. This time we will be pursuing our endeavors to reproduce the conservative Q-learning for offline RL. And well, I believe we are past the literature review period of the paper, but just to make sure, does anyone have additional comments or maybe some obscure parts regarding the paper first before we get into the code part?
No.
Sounds like not much. I do have maybe a little. In the end, I'm not really sure if it changes depending on the action space being either discrete or continuous. But there is this. They basically have a CQL H, right? And there is a CQL. Which one was it? Row, I believe.
Yeah.
And the CQL row, they choose the mu as a uniform distribution, it seems. Or is it the past policy? Yeah, this part is quite confusing for me. Does anyone have like a quick rule of thumb?
So in what I've tried, which I think actually might be slightly wrong, but it seems to have worked, is I've tried the one where they put row as a uniform, like random policy, I think. But actually what I've done, so if you go into their code, they do some importance sampling for kind of selecting actions from a random policy and from the policy that's being trained. But I just, for simplicity, just so I could like make a start and then make it more complicated, I just ignored the importance sampling bit. And all I do is sample actions from my current policy, take the log of the sum of the exponents of the Q values. And that seems to work relatively well, surprisingly. I'm going to share my code later, but
okay.
It kind of seems to give all right results.
Nice. Well, since you brought up their code, I believe you're referencing this part.
That's
probably.
it. Yeah.
Yes. First they assemble from the uniform, and then they add some additional, well, let's say, actions. No,
Yeah.
actually Q values for the action sample from the current policy. Which reminds me, in this case, in this part, notice that they use the new current action tensor, this one, which was sampled using like the next observation. But here they use the current observation to obtain the Q value. So I was wondering if this was on purpose or if it's...
Yeah, that doesn't sound quite right, does it? It should be next observation. Or are they using, is that where they're using a previous policy?
I believe this part is the current policy, right? Because they sample using this get policy actions of self policy.
Oh, and it's next observations there as well, yeah.
So here they use next observation, but they compute the Q value with respect to the current observation and the next action. So since their objective is not really to maximize something here, but just to have enough data to take this expectancy, right? So yeah. I guess in a sense, it shouldn't really matter which action they take. So maybe I was wondering if that's the logic they were following.
Oh yes, because it's not necessarily from a particular policy as such. It's just any action that's kind of not in the behavior policy.
Yes. So whatever this part, these two, well, Q value function outputs, the objective is to actually minimize it. So if the action, even if the action do not correspond, I guess in a certain sense, the objective is still achieved.
Yeah.
So maybe
I think so.
maybe some additional experiment should help us understand more better, I think. Well, this part, so I believe you use the CQLH, right? The one which uses the log probabilities.
Yeah.
Yeah, okay. Of the past, the current policy, to be more rigorous.
Yeah, so I don't actually know if that's the right thing to do, but essentially that's what I've done, and I might actually, what I'm going to try is my next step is kind of the importance sampling bit by using a uniform random policy and the current policy, just to see if that maybe stabilizes things a bit. But
Nice.
just my kind of very simplified, broken down, easier to understand version is just essentially using the current policy for the left hand side of that first bracket for my Q values.
Understood. Well, I believe I tried. Oh yes, go ahead.
Oh, sorry. Just have a doubt on how to calculate the second term, second term inside the square bracket.
This part or this part?
No, sorry, it's an equation 4. Oh, sorry, you guys are talking equation 3. It was
Equation
equation
3.
4. Yeah.
Okay. The second term?
Yeah, yes.
Oh, so
this one?
No, inside the square bracket,
Okay.
expectation
This
over
part.
pi beta. Yeah.
Oh, well, it's the expectation of the
action squared over pi. What is the action over s? Yeah.
Okay, no problem. So this action here is a sample from the pi beta hat, which is just a simple for the behavior policy, the empirical behavior policy that was used when sampling the data set. So this is basically the actions of the expert that we just take and compute the corresponding Q values and then average over all the actions. And in the source code, this will probably speak to you more. Since we have the action, just a second. Okay, maybe. So this is where they get the observation from the expert dataset. Okay?
Okay.
And here are the actions, which are sampled from the pi hat beta.
Okay.
And what they do next is compute, you have Q1 pred, which takes the observation in actions, and also Q2 prediction, since we have two Q functions in soft actor critic. So that's our QSs, and the last thing they do is to subtract it here. Well, for the first Q value function, we have the first loss, min QF loss, which is the one we want to minimize, so this part.
Okay.
That's the one they compute up to here. So that's the first term. That's the second term. So they take the mean. And that's basically how they do it. Hopefully this helps kind of.
Yes. Yeah, definitely. Thank
you. For the discrete case, I believe you are more interested in Atari games, right?
Yes. Yes.
Yeah,
so we can do the same thing for discrete, right?
Well, in the case of the discrete one, I believe we have the action of the expert as a one-hot vector. So all we have to do is to pass the S's to the Q function, and it returns the value for each action for the given state, and multiply it by the one-hot vector, so we get only QSA, and take the mean.
All right. Okay.
I am pretty sure if you... Okay, in the monthly dev discussion, we have this, there was a CDart, user CDart that...
Yes. Yeah.
Okay, he has in the thread, he has a pretty nice computation you can check for reference if needs be.
Yeah. Sure. Yes.
So we actually made basically, we went through all the important parts of the soft actor critic plus CQL, I guess. And well, in my case, I basically followed almost the same method as the original authors. So up to here, we have the default soft actor critic, like loss computations. And then following the one with important sampling, I believe, CQLH, well, we have the uniform actions. In my case, I, well, corrected for the next observation instead of using the same observation. So maybe that's actually what's killing me. Just to make sure. And here, okay, so this is just without the logarithm and with the logarithm part of the policy, the log PSA. And well, same computation, subtract the second term, multiply by the arg min q weight. Actually there is a, this part is quite, just a second. What about, Alex, what about the default hyperparameters you used? Have you followed these ones?
Yes. So I have tried. I've tried two versions. So because they mention.
Maybe you can share your screen.
I can try. Yes. Bear with me a second. I've got. How do I do that? Your entire screen. Okay, I think I'm. Oh no, hang on. Can you see my screen now?
I believe we should, just a second. That's weird.
Seeing the meeting screen.
Yeah, I'm on. Let me just.
Okay.
Okay, it's back.
Okay, so can you see my Outlook at the moment?
Yes.
Okay, so I have to. That is really annoying. That. How do I stop that? So I have to log into my workstation at uni because my laptop is powerful enough to do stuff.
No
so ignore all of this. I'm just running experiments in the background. I'm running 5 at once, which is why it's taking forever. So I try and use. So the main hyperparameters we've got are the learning rates for the actor, which I have done as 3 times 10 to the minus 5. But I've also, when they talk about Hopper, which is later on, they say that they sometimes use a slightly larger learning rate for Hopper.
I see.
So 1 times 10 to the minus 4 seems to be better on some experiments, for example, Hopper medium. So I've kind of played around with both. What I did manage to get, which I will try and show you, is, so there's a lot of stuff in here that I've just been recording just for my own record, so just ignore a lot of it. So this is me trying to train Hopper using the medium expert dataset. And here I chose the smaller version of the actor hyperparameters.
So the smallest one. Okay.
Yeah, and so this is, so what happens here is I do 5,000 gradient updates, and then I run the current policy in the environment 10 times and get a return and take the average. And that's what each one of these is. These are blue, I think they are. And then this orange line is the 100 moving average. So obviously for the first 100, it's 0. And then this is where it starts.
Yeah, sure. Got it.
Yeah, and so it slowly improves over time. It's not too bad in terms of stability. I use a batch size of 256. The actor and critic networks are both 2 layers with 250 nodes each. And then my target network's update parameter is 0.005. And it's using a fixed update. This part here, and I'm doing that. And I think that's pretty much. Oh, and then the minimum entropy is just minus what if you so they use the same soft actor critic as the people who came up with the soft actor critic, and for their minimum entropy term, they just do minus the number of actions, which in this case is -3. So you can put 0, and that seems to work okay, but I just went for -3. So that's essentially kind of what it looks like. And then what I do afterwards is I run 2 versions of the trained policy. I run the latest one, so whatever the policy is at the end of this is run, and then I run the policy which has the best moving average, and then I plot the results here. And then I do that for about 200 runs, and so you'll see that it's relatively stable, but it has a few dips.
Really? Do you evaluate in deterministic mode?
Yes, I think so. Let me have a look.
So it's probably the stochasticity in the environment in that case.
Yeah, let me just have a quick look.
But that's quite some nice result indeed.
Yeah, it's not bad. And I'm currently trying to train the Walker 2D one. I don't think I've got any graphs at the moment, but I managed to get. Oh, where's it gone? Hang on a second.
Hey, hey, what's up, guys?
That's my result for Walker 2D, and so it's not too bad, but again, it's got some dips from these instabilities that I was kind of mentioning before.
I see. Could you please show us the part where you compute the CQL related terms?
Oh yeah.
That's probably the meat of the.
Yeah. Okay, let's try and create a bit of space here because this is all over the place.
Really dive into the code.
Oh yes, lovely.
Yeah. Mm-hmm.
Okay, so here is my critic network, bog standard. We're all familiar with PyTorch, are we?
Yes.
Okay, good.
Actually, we also did the soft actor critic, so I believe network structure and even the Bellman update should be mostly understood already.
Oh, okay, cool. So I've got my critic network here, just 2 layers, nice and simple. Then I've got my actor, which is Gaussian and has the reparameterization trick somewhere in here. So you output a mu and a sigma, and then did you know that there's a built-in PyTorch functionality for sampling from normal distributions?
Yeah. We have had the fortune of contending with that function. Yes.
Okay. So I've got one that does with some randomization and one that does it without. So you've got some exploration going on here. Then
have the correction for the squashing.
The squashing, and then that part where you work out the log probability using that closed form formula they have in the paper. So I initialize the networks. This is the auto tuning of the entropy parameter. So that's just starting it off as 0. Blah, blah,
so
blah.
now there is like alpha and alpha prime. So let's pay attention.
Yes. Okay.
Also, quick question. Could you go back to the critics definition real quick? So I noticed you have 2 optimizers for critics 1 and critics 2, right? But since you're using the same learning rate, would it make a difference? Or what, is there a difference between using different optimizers versus just using one single optimizer for the alpha and critics?
So you mean why is there like 3 different learning rates?
Right. Oh, I see.
Q.
So you have 3 different learning rates. I see. Okay.
Yeah, one for the actor, one for the critic, and then one for the alpha.
I see. Thank you.
You can actually do this in a slightly more elegant way. I've done it in previous versions where I've just had a critic network output 2. It's like built in. So instead of initializing 2 critic networks, you initialize one network that has 2 outputs. You can do it. You can do it either way, I think. Blah blah blah. Choosing an action is just from the agent bit where you sample from your probability distribution. Sample a mini batch. That's just the normal critic update with kind of the minimum of your 2 target networks. So this is all that I've done for my extra CQL bit, which is a very simplified version, but it's not doing too bad. So I repeat the state that I've got. I've done it 100 times. They do it 10 times in the paper, but I've done it 100 times. Sample sample an action for each repeat of the state. Then work out the Q values for each of those state action pairs, and then do the log sum exponential of those Q values, which is this bit. So that's that bit. And then use the actual state and action from the batch, from the data, and just do the Q values for that, which is this.
The expectation, okay.
So you basically, okay. You sample only from a uniform distribution, the actions.
No, I'm actually sampling it from my current policy.
Oh, okay, I see.
Yeah. So that's where when I was going through the Slack channel and I noticed that it's supposed to be sampled from a uniform, where I was kind of surprised that even though I've sampled it from my current policy, it still seems to be okay, which is a bit weird. Maybe I'm just freaking it. I don't know.
Actually, they do say sampling from the past policy is more stable on high-dimensional action spaces, I believe, just at the beginning of the page 5, but okay.
Oh, yes. Okay.
Good to know.
And then, so I've got this bit again is that bit. I'm not really taking an expectation or anything there. I'm only using the state and the action. So it's not really an expectation. It's just one value for each state action in my batch.
I believe it's the same result as in Q1. You have at line 124, I believe.
Yeah.
Okay.
Yeah. And then, so this is where it kind of gets a little bit like messy, but essentially this is your normal Bellman update. And this is the extra bit. So this is this bit. This is this bit. And then I've taken the mean of that minus that, and then times it by alpha. And that is my loss for my critic.
I see.
And then the actor loss is just the normal actor-critic, soft actor-critic stuff, and the same for the automatic entropy tuning, and then a soft update of the target networks.
It's really simpler indeed, not like the.
Yeah, so I try.
Offers.
Yeah, so their stuff, I think they allow a lot more customization, if you like. This is quite restricted in what you can do, whereas they let you choose things like what kind of do you want to do, the CQL-H or CQL row version and all sorts.
Well, even beside that, they use instead of, well, in your case you just have self alpha prime, right? But in their case they have the temperature, and additionally they have a mean Q weight, a hyperparameter, which is not really specified. So that's
Yeah, so this alpha prime is specified earlier on here.
no.
That's
In your version, yes, but in their version,
I see. Yes.
do they have the alpha prime? Maybe I can share the screen really quick.
Yeah, I'll stop. Hi, Costa, by the way. Nice to meet you.
Yeah, nice to meet you too. Glad you could join us.
Yeah, it's good. It's been interesting so far.
Wait, so Ross, on a very high level, do you feel that Alex's implementation is in line with yours?
Conceptually, yes.
Okay.
Simpler, probably. Simpler is better.
I
think I shot myself in the foot trying to following exactly the offers. So here were the coefficient I was talking about. You can see that beside the alpha prime that you use, this is basically the same thing. They also have this mean Q weight functions, which they, the only mention I could find for them was in the README. Either use 5 or 10, but there is no real reason provided that supports such kind of practice.
Yes,
maybe it's to tune the soft max, the soft Q value, or something like that.
Yeah, so you tend to find this. You've probably come across this yourselves, where when you delve into the code, they have these little sneaky additions that kind of come out of nowhere. Like when they clamp things and they don't mention anything about it in the paper, it's like, oh, we clamp this for stability, and it's like, oh, okay, fair enough. But like you're kind of tweaking things just to make it work. But I suppose it's more art than science in some respects.
Empirical science.
Yeah, exactly. Yeah.
Okay. I will definitely try it with the simpler version.
I will. Yes, I will. I'll share this code that I've got as well. It's not perfect, but it gets some half decent results for the expert, medium expert, and expert data sets.
It's something. Where were those curves?
Oh yeah, quite a long paper actually, considering the appendix.
Yeah.
They try to put a lot of proofs, but those proofs don't really give a lot of intuitions.
Yeah, it's more for completeness. I think I skip those.
Yeah.
Yeah, so my training curves aren't quite as smooth as that, but maybe some important sampling might help.
Wait, so the important sampling part just consists in adding the log probabilities?
So the important sampling bit, there's a section at the end of if you go to page 29 of the paper, they explain how they do the important sampling bit to calculate the log of the sum of the exponentiated Q values. But I haven't tried this bit yet. That bit.
The one on the bottom? This one, right?
Yeah. Yes. Yeah, in the computing log, some over the A, etc.
Oh yes, I remember that part. And the current policy pi using alongside. Okay. Well, still does not explain where the log, the minus log policy they have somewhere here, I believe. Yes, here. Important sample version. Well, for each, well, slightly different from yours. Here they sample from uniform, and then they sample like the actions from the current policy for the current states, actions for the next states, and then they do the corresponding Q value computation. And that's what become concatenate everything here. And that's the version without important sampling. So I believe if we were to, your version only uses this one, I think.
Yes, at the moment, yeah.
Yes, and well, the current policy. But well, since they have augmented with all this data, additional data, with the important sample version, you can notice that all they do is subtract the log probability corresponding to each method of sampling, basically. But I do not think... Does it appear here? Well, they say the expectation. So that's where the log hides, I believe.
Oh yeah, because it's the log of a ratio, so you take the difference. Yeah, it's it's always quite hard to try and extract exactly what it is that they've been doing in the code. It's particularly this group as well. When you get around to looking at Bear, you'll notice it's the same kind of problem. But when it comes to BCQ, their code is much more straightforward to follow.
Okay. Yeah, I would say CQLs, especially with the discrete action space, it looks pretty straightforward. But for the continuous action space, they have this weird, formula that you have right in the shared screen.
Yeah, and I'll try it, but it just seems that if you're dividing, so if you've got your Q values, then you take the exponential of that, and then you divide it by what looks like it's a probability essentially of taking that action in that state. Isn't that just going to make things like that term enormous if your probabilities are really low? I don't know. I just think it might balloon, but I haven't tried it, so I don't know.
I guess further experiments are required.
Yeah. Yeah.
Sure. Have any of you tried CQL with Atari games by any chance?
Not yet.
No, I haven't yet. No.
Okay.
I believe you got something working on your side, I think.
I got something only on the DQM part. Sorry, I'm late for the meeting. I had an interview that was not wrapping up as took a little longer. Anyway, so I got the CQL kind of work. Well, CQL doesn't really work for me. Let me present this part of the screen.
I did see some learning on breakouts, around 40 at least.
So that's actually DQM. So that's not CQL.
Okay.
Can you see my screen?
Yes.
Okay. So basically, I try to run. I basically just take the DQN, our DQN code, and just load the data from the D4RL Atari library, and load the data, and then just run it. So DQN actually works quite well in the beginning, but then it starts to deteriorate later. And the way that I set it up is to basically, maybe let me enlarge this real quick. So everything else is pretty much the same, except I just have to replace the instead of sampling from the replay buffer, I sample from the data loader and load them into GPU. So that's the only thing that I have to do that I have to do.
And does the agent still sample from the environment?
What do you mean?
Well, the curves, how do you obtain the curves?
So the curves is basically, so if you the agent only do evaluation. So if you see over here, we still sample an action from the agent to the environment. So we execute it in the environment, and if the episode finishes, we record the episode. If it's done, we handle it correspondingly. So, but importantly, the observation rewards and dones, there's no replay buffer, so it doesn't add to the replay buffer.
Okay, so that's the difference, basically.
Yeah. So the only thing I have to do is to change this and remove the replay buffer. And it's able to get pretty decent results initially, but then it starts to deteriorate. I also think in order to evaluate this more, I guess, fairly, it's probably a good idea to do some other, to record some other metrics. I remember in the CQL paper, they tried to log something like the Q values. So you get a sense of how much is the Q value overestimating, things like that. Yeah. And lastly, I tried it with CQL. So I'm looking at the code from CQL. So they're using quantile distribution agent. So not exactly DQN, but they essentially calculate the loss, and then they add the CQL loss to the quantile DQN loss. So I'm basically adding this CQL loss to the DQN loss. And from the code perspective, I basically modify this part to match what I have. So what I have for the DQN. So this up until this point, everything is the same, and then I basically try to get the old values. So if you're looking at the formula, these are the Q values. These are the old Q values from the data set.
Yep.
So I get the mean of them, similar to how the authors got the mean. So they basically get the chosen Q, and then they got the mean, and they call it the data set expectation, which I guess, is expectation of the Q values in the data set. And then they have this negative sampling. So that's basically torch some, basically calling the default function and getting the old Q values and sum them up. And lastly, we have the mean Q loss, which is just the sampling minus the dataset expectation, which corresponds to this part of the formula. And then this is added to the loss when I do the backward. So the CQL, at least the implementation that I have, performs much better compared to offline DQN initially, but then it starts to plateau over here and doesn't really perform nearly as well as the regular offline DQN.
Yeah, it took me a while to get mine to well, I managed to get it working, and then I changed I think I changed the learning rate, and then it tanked, and then I changed some other high parameters, and it started working again. So there's a lot of tuning to be doing. And the problem is, of course, it takes so long to run everything that you don't know if it's not working because you haven't run it long enough, or because it just doesn't work.
So that's actually something that I'm wondering. So by looking at the paper, it looks like for the Atari games, they actually converge pretty fast, but that doesn't seem, I find that unlikely. So if you look at their offline RL for Atari games, they only train for 100 iterations, right? Before getting good result. Only training for 40 iterations. Does that mean 40 gradient updates? And then they're able to perform get 100.
I'd be very surprised. Oh, I don't know. That doesn't seem. That seems very low.
That's
Yeah.
unlikely. The iteration probably stands for something like 1,000 updates, probably.
Yeah, you think so, right? Because quantile DQN, I don't know how they do it, but doing 40 gradient steps to achieve this level of performance is very unlikely. Like they're probably, you see they have a lot of shakes, they have a lot of curves around here. I think there are more like turning points in this curve than 20 data points over here.
Yeah, I reckon they're probably doing like 5,000 updates or something like that.
Yeah, let me read it. So as a function of the training steps, x-axis. Oh, in setting 1, what does that mean?
It's below.
Huh?
Just two lines above the table, setting 1.
Like over here?
Mm-hmm.
Oh, yeah.
They just
Yeah, that doesn't really tell me. Well, so at least according to the paper, it almost sounds like this is just a training iteration, like the gradient steps, but that doesn't quite sound right.
Oh, okay. I think I may have found it. I think it's 5,000. So if you go to page 30, at the top, there's something called number of gradient steps, and then the last sentence is, it says, for our experiments, we use 1 million gradient steps for all D4RL domains and followed, oh no, sorry, that's just D4RL. Oh, and followed the convention from Agar et al. To report returns after 5,000 gradient steps for training for the Atari. So,
Oh my god. Okay. So 5x, did you say 5,000 or what does it even mean?
oh no, that would be 5K, 5 times gradient steps, 5x.
Oh
5X.
yeah. Report the returns after 5x gradient steps of training for Atari results. Like the sentence doesn't make sense.
It could be a typo.
I guess then it would make, although x and k is pretty far away from each other.
Yeah, that's true. I'll see if there's anything. So when they show the graphs at the top of page 16, the learning curves, it's obvious there that what they mean, they've got gradient step and they have 0.2 million, 0.4 million.
Yeah, those make sense.
And that makes sense. But when they call it iterations, I don't know what they mean. I wonder if it's what they've got in the Agarwal paper, because they mention iterations. Each iteration in the optimistic perspective on offline reinforcement learning, each gradient, each iteration corresponds to 1 million training frames.
Okay, so that's
What?
wait, each iteration. So this is like 100 million.
Potentially, actually,
As they usually train them to match the ordinary performance. 100 millions, yes.
That's crazy.
Well, that's what we do anyway, right?
Yeah, well, for most of the Atari games, actually 10 million is sufficient for a lot of algorithms. But
Well, in the papers, they usually make it until 100 millions.
yeah, it makes sense, I guess. But yeah, 100 million sounds much more reasonable than 100 iteration. 100
20 gradient updates. That would be genius.
Yeah, I was looking at that and I was like,
You have
really?
to do that over the whole buffer to have even a slight chance
Yeah.
of working.
Yeah, right. But even if you do that, the learning rate would be too low to learn anything useful. 100 times the learning rate is, yeah, it's still too low for you to learn anything.
Well, maybe with enough data.
Yeah, I guess. But yeah, so unfortunately, the first stab at the reproduction is not particularly successful, and my CQL. Okay, so maybe CQL is not performing well over here. This may be just not training it for long enough, and maybe having a sort of pessimistic Q value estimation actually made the performance worse. We still haven't seen the turn that's sort of shown over here, so I guess I'll stay tuned.
And I think the quantile regression DQN, I think is performs stronger than your kind of bog standard one, but I don't know how to code it.
Yeah, that's a good point. Yeah, so quantile is supposed to perform much better, but I think it's probably not significantly better than C51. So let me see the quantile.
No, it's actually quite better, I will say.
Quite better, really? Okay.
Yes.
Maybe probably worth it to look into as
It's
whatever.
C51 on steroids.
All right, so let me see. So yeah, well, it has one particular instance where it's a little performing better than C51. Definitely improvement, but I will be kind of skeptical of. Well, definitely improvement, but
I am. What was it again?
overall probably outperform DQN quite a lot because this is DQN.
Yeah.
Well, in any case, QR DQN addition is probably about the quality of the distributional estimation. Because instead of using like if I remember correctly, in C51 we had atoms, right? 51 atoms. With QR, the quantile regression, they get rid of the atom to have something more smooth and continuous for the estimation of the Q.
I see. So maybe instead of
yes, like a relaxation.
Okay, that sounds like a really good idea. So instead of like actually what we like something that we have like over here having this sort of return, instead of being discrete values, it would be just like a curve, like a normal distribution.
Yes, that's the idea.
That's very interesting. Okay. Yeah. So
it's quite hard to understand. I find that one.
Just a comment, but how is your dark mode? Is it an extension?
So all you have to do is to go to profile and you have to add a comma.
No, it's okay. But see
that?
Wow.
It's kind of something that they didn't really have until you do this really weird thing, add a knife thing in your profile introduction.
I see. Hey, if you could just go back one page before.
Yeah.
I noticed that it also inverted the color of the environments.
Yes, that is true. So they're supposed to look like this.
Okay. Yeah, that was just.
Yeah, it's definitely a little strange. Sort of on a related topic to QR DQN. Have you guys seen this paper, Revisiting Rainbow?
In the reading stack. It's in the reading stack.
Oh, I see, yeah. Yeah, so they basically tried Rainbow on some simpler games, which I thought was pretty interesting because Rainbow has but they also open source their code, which is something that I really like.
Nice.
Yeah, but in any case.
Do you have any highlights? Any spoilers?
if at some point we decide to go down the quantile agent path, they appear to have,
TensorFlow, right?
yeah, it's built on TensorFlow, but probably a good reference.
This one seems to be using JAX even.
Oh yeah, fancy boy, right? I think probably the best implementation reference though is the DQN-Zoo. I don't know if you guys probably have already seen it, but they basically have a reference implementation for all of the DQN algorithms.
Nice.
And they have a single place that reproduces this, which is amazing. Right?
Yeah, that's good.
Amazing.
Yeah, so I guess they have to tune it such that Rainbow performs better than everyone else.
Yeah, always take it with a pinch of salt.
Yeah, always.
Especially the offline stuff. Before they had the default RL datasets, I mean, it was anyone's game really, because you could just train an agent yourself and then put some random noise into the data and then try your algorithm, and surprise, surprise, everyone gets state-of-the-art results because they're not using consistent data sets.
Yeah, for sure. So definitely really like the D4RL sort of as a benchmark.
Yeah, it's definitely a good starting point at least.
Mm-hmm. Yeah. So I noticed that when you display your code, Alex, have you been using Matplotlib to sort of print out the episode rewards and stuff like that?
Yes, yeah, just basic stuff.
I see. I don't want to sort of advertise it, but sort of wait and buy it.
When do we chill?
Yeah, we use it to do the experiment management, and we don't in a way we don't have to worry about the plotting anymore, which is pretty nice.
So sorry, what was that? I missed the first part.
So have you used Tensorboard before?
I've heard of it. I've not used it.
Yeah, so basically you can just, so instead of like print an episode reward, right? What you would do, so usually like without Matplotlib, right? You just have this print statement.
Yeah.
So that would produce stuff like this.
Yeah.
And then that's probably usually the first step for experiment management. But then you can create a writer by using Tensorboard, and then it'll give you this, which is going to take some time to spin up a Tensorboard sort of instance. But basically, weight and bias is sort of a service that allows you to to do experiment management, but they have really good integration with Tensorboard. So specifically, this is all the code that I need to do just to initialize the weight and biases project and replace the writer. And then I get this. I get this thing that I can look into. I can go to this address on my phone. I can check out the videos of the agents playing the game if I use a monitor wrapper.
Cool. Yeah. So I'm still quite
automatic. It also does the smoothing for you.
Yeah. So you can click on this and do a little bit of smoothing.
That is amazing. So I'm still quite new to Python. So when I did my masters, it was in statistics, and they use R a lot. So I'm sort of still making the transition from R to Python, but that looks really good because I just do basic print statements and basic graphs, and it's a bit fiddly and it looks nowhere near as good as that, and it doesn't give me as much like meta information. So I'm definitely going to look into this.
Yeah. Just maybe I feel you might be interested in to try it out because it really makes our lives easy. For me, it has made my research a little easier to keep track of. Yeah,
that's good. It's kind of, it might help with another problem that I have with offline DRL is stopping criteria. I don't really know what the best, do you stop it when you've got a good running average, but then what's the running average? Is it 1,000? Is it 100? Because you can't use the loss like you can in kind of more supervised learning stuff, because your loss your loss is kind of based on bootstrapping and stuff, so you can't just have like an evaluation loss. So stopping criteria is definitely something I've been considering. I haven't really got anywhere with it.
Well, stopping, we usually train for a fixed number of time steps or gradient steps. Or are you talking about something else?
Yeah, so that is one way to do it, but sometimes the latest policy isn't necessarily the best one, because you can overfit your data, can't you? So and it's more the case in offline reinforcement learning, really. It's kind of like analogous to the overfitting that you get in supervised learning. And when you're training your offline agents, so say that you do 5,000 gradient updates before you then evaluate your policy, you can then decide, well, how many times do I want to evaluate my policy? Do I want to just do it once, or do I want to do it 10 times to take an average, or 100 times to take an average? And that affects what your stopping criteria is as well, because if you're doing it over 100, then you might just want to take the policy that has the highest score. But if you're only doing it over 1, then you don't want to do that, because you might just have had a fluke peak in the score.
Right. Yeah, that makes a lot of sense. Yeah. Another sort of way that I've done that personally is to basically, well, instead of evaluating every let's say 5,000 gradient steps, I just evaluate after every training. So essentially you get a stream of evaluation scores, and then you see that you can use it. So instead of seeing this episode reward, you'll just see a stream of the evaluation reward, and then you can just say, oh, if the evaluation score, I guess the last 10 evaluation score is over by this much, then it'll be your stop condition.
Yeah, so I've tried that as well. I've tried doing kind of like one evaluation per gradient update as well. So yeah, sometimes I've had some really good results and sometimes some dreadful ones. So
I see.
Just a quick question. What value did you use for alpha prime again?
What value did I use? It was 5, I think.
5. Okay.
5, yes. It's whatever's in the paper at the end of the paper, the last page on the right hand side of that column. Yeah, alpha equals 5. Bear in mind that that might not be the best for what I'm doing, because I'm not doing importance sampling or anything like that. So I guess that's another hyperparameter to play around with.
Okay. Well, just for reference in any case.
Yeah, it's kind of like a good starting point.
So, I guess we have. Oh wait, I had also a question regarding the discrete action spaces.
Yeah.
Costa, did you? How is alpha handled on your side?
Alpha? Are you talking about the sort of the
Alpha in equation 4?
Yeah, I never seen the so from over here, I don't see where alpha is.
They call it alpha prime just to confuse you.
Also not seeing.
Oh.
They say
that's
in
those.
both cases it is set to 0.5, so maybe that's why.
Sorry.
In the alpha you have highlighted on the next line. I think they explain why there is no alpha.
Okay, rainbow are parameterized by an exponent, but in both cases set to 0.5.
Or is it something different?
No, that's just the
That's
alpha
another
for
alpha.